Hey guys, today I'm just going to kind of go over the intro to logarithmic functions. Okay, something important to note. Logarithmic functions and exponential functions are inverses of one another. So if you take the inverse of an exponential function, something like 2 raised to the x, you should get a logarithmic function. Okay, so here's the basic idea. If you have an exponential function, such as we do right here on number 1, where it's 2 raised to the x, then the inverse of that would be f, okay, I cannot write right now, would be, I'm going to have to make this pen a little bit smaller, f, okay, now, it's kind of hard to see because I suck at writing, but what I just wrote right here is f inverse of x, so that little tick mark, here I can write a little bit better over here where I have a little more space, means inverse, okay? So when you see something that looks like this, it just means the inverse of your function f of x. So it just means this idea that, hey, anytime you see this, it's the inverse function of this, okay? So the inverse of 2 raised to the x is the logarithmic function. Since this was exponential, because I have x in the exponent, the inverse of it is a logarithmic function. So you say log. Now, go back to your original function, okay? What is the base of this guy? 2, right? So you know what the base of your log function is going to be now? 2. The base stays the base. And then what goes inside the log is the exponent. Bam. That is your inverse. Okay? So like, let's look at problem number 3. Alright, it's the same type as problem number 1, so I'm going to go over it. Okay? It's going to be log, I should write f of f, the inverse of f of x, so f of, you put a little tick mark there, just means the inverse. Oh, it's not a tick mark, it's a -1. Sorry. Tick marks represent derivatives. Whoops. Alright, it's f raised to the -1 of x. Okay, that means inverse. My many apologies on that. I'm an idiot. Sorry. So f raised to the -1 of x. F raised to the -1 of x means inverse. Okay? So, f raised to the -1 of x, the inverse of this function is log. Okay. So right now the function is an exponential function of 6 raised to the x. So the base right now is 6, so the base is going to stay 6. And then you just put your exponent inside. And there you go. That is the inverse function. All right, well, let's look if we went backwards. Look at problem 5. Log base 5 of x. Okay, so right now we have a log function. So if the inverse of an exponential is a log, then the inverse of a log is an exponential. So we're going to take the inverse. So f raised to the -1 of x is equal to, okay. So guys, look back here to how we went from exponential to log. The base became the base, and the input became, the exponent became the input. So we're just going to do that same thing. The base is going to stay the base. We're going to have 5 raised to the input, which is x. And there we go. All right. Okay, let's move on down. Let's go to this next section of problems. Write the equation of the inverses of each equation. Then graph the function, the inverse, and y equals x on the same set of axes. Okay, so just right here. So this is our original function. Log base 4 of x. So what would be the inverse of that? Well, that's pretty simple. The inverse of that would just be 4 raised to the x. That's what we just covered. Because the base stays the base. So the base was 4, so the base is 4. The input from a log becomes the exponent on an exponential. So, let's choose some very simple numbers. Let's do, I don't know, -2, and you're going to see something here. -1, 0, 1, 2. Now, there's a reason I chose -2 through 2. All right, you're going to see it happen here in a second. All right, so we're going to hold off on plugging this table, and then I'll explain why in a second. Okay. So let's pull up our calculator, turn it on, if it will. Come on, you stupid machine. Okay, so y equals, okay, now, for me to type in log base 4, I have to do a weird thing, okay? For you guys to type in log base 4, I believe you can hit math, and if you scroll up, you'll get to something right around here. It's not on my calculator, but it's on your calculator, called log base. Alright? You should definitely take a moment and find it. Okay? That will help you a lot if you can find log base. It's not on my calculator. All right, because I have an older calculator, but it is on your calculator. Okay, so what I have to do is called the division property. No, quotient rule. Sorry, I have to do not even quotient, power rule. My apologies. Basically, it's this idea that if I want to do log base 4, when you hit log in a calculator and there's no base, the base is understood to be 10. So right now, Mike, when I hit log, this base is 10. But I don't want base 10, I want base 4, so I have to say log of x divided by log of 4. Okay, so now what I just typed in is the same thing as this right here. So I'm just going to go to the table, and I'm going to get that at -2 through 0, the outputs were errors. Interesting. And then, so I'm just going to put an E to represent error. That was supposed to be an E. E to represent error. E to represent error. And then 1 is at 0, and 2 is at 0.5. Okay? So, I'm going to go graph this. Now, wait a second. How am I going to graph errors? Well, do you guys notice something? I have an error at -2. I have an error at -1. I have an error at 0. Where does my error stop happening at? Well, at 0, right? Think about this for a second. Think about it with me for a second. If these two are inverses of each other, and we know the exponential has a horizontal asymptote at y equals 0. Do y'all remember that? We just took a test, so I hope the answer is yes. I do remember that. Okay? The horizontal asymptote is y equals 0. Well, if inverses are really just reflections across this line, y equals x, then if I reflected the horizontal asymptote across y equals x, what kind of asymptote am I going to get for the logarithmic function? I'm going to get a vertical asymptote. That's right. And it's going to be not at y equals 0 now, but at x equals 0. Okay? So, for logarithmic functions, you have a vertical asymptote at x equals 0. Okay? And now I can kind of talk to you about why that is, just to give you a little more algebra understanding of why that is. Real quickly, think about what a log function is. Okay? A log function says log, let's take this one, log base 4 of x. Alright? Let me explain what logs do. What logs do is they simply allow us, so let's say that equals y, okay? The answer to this question is going to be 4 raised to the y equals x. So in other words, when you type in a log of a calculator, let me show you an example. When you type in a log of a calculator, something such as log of 100. Okay, so first off, before I press enter, let me talk about a couple things. You know that when you type in log, the understood base is 10. Okay, when you just type in log in a calculator, the understood base is 10. So right now, you're about to calculate log base 10 of 100. So you are inputting 100. Okay, the calculator is going to do this. It's going to look at your base, which is 10, and it's going to ask itself, 10 raised to what number is 100? And that's going to be your answer. So it's going to ask you, 10 raised to what number is 100? And that answer is 2. Okay? So that's what this question is doing. It's saying log base 10 of 100, 10 raised to what number is 100? And that is 2. Okay? So if you go back over here and you think about, okay, so then why do I have a vertical asymptote at x equals 0? Like, why am I allowed to say, other than just the fact that I can think about how exponentials, flip and they're inverses of one another. So if exponential has a horizontal asymptote of y equals 0, then the inverse would have a horizontal asymptote at x equals 0. I get that. Vertical asymptote at x equals 0. All right, I get you can think that way. Maybe you just want to know it based on the algebra. Okay, well, ask yourself, log, and the base isn't going to matter, but I'm going to go ahead and keep the same base here, 4 of 0. Is there any way that you could raise 4 to some number, okay? Is there any way you could raise 4 to some number to get 0? Is that possible? In other words, could you raise 4 to a power and get the output of 0? No. That's why we have a vertical asymptote, because I can never input 0. Because 4 raised to, there is no number that could raise a base 2 to get 0. Okay? So that's why we have a vertical asymptote at x equals 0. Because there is no way that I could raise a base to a number to get an input of 0. So I have a vertical asymptote at x equals 0. Alright? So I'm going to plot these. 1 is at 0. and 2 is at 0.5. Okay, and then I'm going to cheat a little bit. It's not actually cheating. And I'm going to hit graph, just so I can kind of see what my graph should look like. And bam, so I know I'm going to come up from the asymptote and just kind of go to the right forever. So I'm going to come up from the asymptote and just kind of go to the right forever. So there is my first graph, okay? So now we're going to do my second graph. Well, what's cool about, oh, sorry, we need to do the domain and range. Okay, what does the domain look like from here? Remember, domain is left x values to right x values. So what's the most left x value happening for this graph? That's right, 0. And then what do we do after 0? We just go on forever. But since I don't touch 0, I put a parentheses. So I say 0 to infinity. And then your range in this case is all real numbers. Now guys, that should make sense. Let's stop and think about why that should make sense. Do y'all remember the exponential function? What was the domain every time? All real numbers. So you should notice that all we're really going to do here is switch, because they're inverses. And an inverse is just a switching of a y and an x. Alright? So domain is x's, so it becomes the y on the inverse. And range is y, so it becomes the domain on the inverse. Okay? So that means I can go up here and I can say error, error, error. So all I'm doing is switching x and y. Okay? And I'll get a y value of -2. In other words, these values, guys, what I'm trying to say is these values aren't going to work. You know what? That's just going to confuse you more. We'll use the same x values. We won't just switch points. We'll use the same x values. -2, -1, 0, 1, 2. Oh, I want to change color so you guys can see the different graph. All right, when you plug in a -2, you're going to get, I don't know, some weird number. Let's let the calculator do the thinking for me. Click clear. 4 raised to the x. Second graph. 0.0625 and then 0.25. I gotta get rid of the calculator. Ooh, this video's going long. Sorry, I'll try to speed it up. 0.0625, 0.0625, and then it was 0.25, and then it's gonna be 1, and then 4, and then 16. Okay? So we're gonna plot that. Now remember, exponential functions have a horizontal asymptote at y equals 0. Okay, and so then -2, I get something like right there. -1, I get something like right there. 0, I get 1. At 1, I get 4. At 2, I get 16, which will be up here. And we know that exponential functions, if they're growths, look something like that. All right, and then the line y equals x, guys, you should know is this. It's a slope of 1, and it just goes up. I don't know why I'm dashing it. I could have drawn it straight. And so you should notice, what do you notice about the blue graph and the green graph? They're reflections of each other across this red line. That's really what we're trying to get you to see. Okay, this blue graph and this green graph are simply reflections across the line y equals x, because that's what an inverse is graphically. Graphically, we say an inverse is a reflection across the line y equals x. Okay? All right, let's move on to the back page. Find the following for the given functions: transformations, domain, range, and asymptote of the transformed. Okay. First off, this +3, I'm just looking at number 10, I'm just going straight into it. This +3 is outside of the function. To be inside of the function with the x, you need to be in parentheses with the x. So this +3 is outside the function. So if I'm adding 3 outside the function, that means up 3. Okay. So I went up 3. So I went from looking like this to looking like this. Can you really tell a difference? No! Up 3 doesn't really change much for a log graph. Okay? Going up 3 does not do much for a logarithmic graph. The domain. Well, I still have my vertical asymptote at x equals 0, and I'm going to look like this. So, I still have my vertical asymptote at x equals 0. So, I just go from 0 to infinity. Okay, from 0 to infinity. Then the range, well, do I ever stop going down or stop going up? No. So for all log graphs, guys, you guys can remember, for all log graphs, the range is all real numbers. For all log graphs, you can remember that the range is all real numbers. Now the asymptote. This is a vertical asymptote. Does moving up 3 on an already long, infinitely long up and down line change anything? No. So it's just x equals 0. Okay? Going up 3 for an already up and down line doesn't affect it. Okay? But now let's look at a problem like number 11. Problem like number 11 says plus 3 here. Well, that's inside the function. So that means left 3. That is going to change a lot. Because now I'm going to go from looking something like this to looking something like, so, you know, you have your horizontal asymptote at x equals 0. But now everything is shifting to the left 3 units. So now it's not going to be at x equals 0 anymore. I shifted to the left 3 units. So it's going to be at x equals negative 3. And it's going to look something like this. Okay? So my domain now is not 0 to infinity, it's negative 3 to infinity. Okay? And my range is still all real numbers. That's nice. However, my vertical asymptote has changed. My vertical asymptote is at x equals negative 3. Okay? So that's the basic idea. Do be aware on something like if you reflect over the y-axis on problem 13, you're going to go from looking like this. So this is problem 13, similar to it. This means reflecting over the y-axis. You're going to go from looking something like this to something looking like this. So I'm going the other way, and I've actually flipped over the vertical asymptote. So if this is where the vertical asymptote was, and now it's going to look something like this. So that's going to change your domain completely. It won't change your range, but it's going to change your domain completely. Okay? Alright guys, I just kind of wanted to give you a chance to go over that. 15 and 16 are reflections across the line y equals x. Okay? And then basically just tell me the domain and range of exponential functions. Alright? I'm going to say that again. 15 and 16 are simply, the transformation is simply a reflection across the line y equals x. How do I know this? Because those are inverses of one another. If you look at f of x and g of x, you'll notice this is a log. This is now exponential. So that means I reflected across the line y equals x. So now I look at my exponential function. What do I know the domain is for all exponential functions? That's right, all real numbers. What do I know the range is for exponential functions if I don't move it up or down at all? That's right, 0 to infinity. And then what do I know the what kind of asymptote do exponential functions have? Horizontal asymptotes, and it's located at y equals 0. Okay? And don't let 14 confuse you. ln just stands for natural log. That's just where you have a log and the base is that e, that natural number. Okay? That's all that means. You're going to do this problem the exact same way. 14 is not a tricky problem. It's just like number 10. Okay? It's only minorly different because it says natural log. That's it. It won't. The numbers don't change. Other than the -2 still makes it go to the right 2. The ln does not change anything as far as transformations go, or domain, or range, or asymptotes. Okay? It just has a different type of base. Alright guys, let me know if you have any questions. Send me a remind, send me an email. Yeah, have a good day.